joining us. I hope everybody can hear me okay. Today I'll be giving the faculty REU seminar, and I think, I'd like for this to be interactive. If you have questions, feel free to type them in the chat. We could go through them afterwards, or if something's, bothering you with a particular question or slide, just please interrupt me and we could talk about it. I made the presentation into two parts. The first part is a little bit about kind of the work that we do within the I-MRSEC. That's kind of related to 2D materials and wettability. And I tried to pick kind of more interesting things that we do within the lab that are a bit more applied to give you a flavor of where these materials can be used and how they could help society. And then the second part of my talk is more about, myself, where I'm from, kind of the path I took to get to where I am today. And then, I was interested in kind of telling you guys a little bit more about, career choices, i.e. industry versus academia, and kind of discussing challenges I've encountered in my career, and then also differences between the two sectors that you're going to have the choice of choosing once you get your degrees. So that'll kind of be the second half of the talk. So I guess to start, the first thing I should tell you is who I am. My name is Nenad Miljkovic. I am an associate professor in mechanical science and engineering here at the University of Illinois at Urbana-Champaign. I've been here for the past, this is my 6th year, starting my 7th year in August. And I've loved it ever since. I'm actually a fairly new I-MRSEC member. My student James Carpenter and I joined this last fall, and we've been really enjoying the collaborations within the I-MRSEC so far. The title of my talk today is Nanoengineered Interfaces for Enhanced Energy Applications, and you'll see that a lot of the work motivated within my lab in particular is heavily related to energy and water. So here we go. So, the main motivation for the work that we do, there's two kind of core thrusts that we tend to follow. The first question that we try to answer as scientists is understanding nature's design. To give you a good example, many plant species, plants or insects, actually show resistance to wetting. And what I mean by that is if you think about, going outside and looking at common plants within your garden, but a good example is, for example, the lotus leaf, or as I'm showing here, the cicada. If you actually try to put water on these surfaces, the water will just bead off and roll off. It doesn't want to wet the surface at all. And what we're interested in doing in the lab is understanding how is it that nature evolves and why it evolves to actually have these non-wetting characteristics. These surfaces tend to be what we call multifunctional, meaning they have more than one reason to be there. In this case, the cicada wing, for example, these kind of nanopillars that you see on top of the wing enhance or suppress reflection of light. So it's super transparent. So the cicada can actually hide and a predator won't see it if it's resting on a tree. But it's also non-wetting and self-cleaning, in addition to being antibacterial. So you could see there's several functions there that we like to understand how the cicada evolves to achieve all of these functions, and then implement these into societal applications. And I list some of these applications here, mainly energy related, in terms of power generation, building energy, thermal management, you think of electrified vehicles, electrified aircraft, as well as manufacturing, actually. And down here are just some images of the different kinds of projects we work on, whether they're large scale power generation and enhanced condensers, enhanced heat transfer, icing and frosting on heat exchangers, and then additive manufacturing of metal substrates for enhanced heat transfer. So you might ask yourself, why do we care so much about, phase change and water and wettability and interfaces? And I put this slide together to kind of motivate you guys as students to really tell you that this area of research is really what started the Industrial Revolution. And it's actually through development of phase change heat transfer and steam, how steam condenses and how steam boils, that we really kickstarted the Industrial Revolution that eventually developed into the development of internal combustion engines, diesel cycle, auto cycle, electrification of our society, and then everything else that you utilize that's very common in your lives. So like your iPhone, your computer. And we actually still use the exact same methods to generate power today that we used back when this was first invented with the Watt steam engine. And this gentleman right here is actually James Watt. And I think many of you know the unit of Watt in terms of joules per second. It's a fundamental SI unit that we all use. And he was actually very foundational in understanding the conversion of heat to work, to mechanical work. And here I'm just listing a few examples of how this progressed. You know, this image in the middle here is actually the Watt steam engine. Essentially, you're boiling water, you're producing steam, you're expanding in a piston, and that's producing motion, which does work on this rocking arm here, which then rotates a wheel, right? So this is 17th century, before thermodynamics was even developed. People were using these concepts and understanding that, you know, the change of phase between liquid to vapor and vapor to liquid is highly important to societal advancement. This then led to things like steam automobiles and tractors. So for example here, steam locomotive, steam tractor. I'm not sure if any of you have ever seen one of these, but these are gigantic machines. And then in addition to that, if you want to put this within context of Illinois, you know, this is a picture from the 30s of a Caterpillar. I'm not actually sure whether this is a bulldozer or a Caterpillar tractor, but you know, the main reason why Caterpillar succeeded as a company is because steam engines were so heavy that when using them in farms in California, they would actually sink into the ground. And what Holt, the founder of Caterpillar, did was he figured out how to more equally distribute the weight by using tracks instead of wheels. And that actually steam engines were the foundation of Caterpillar, which then drove it as a company and a large contributor to the Illinois economy itself. So I guess this slide is kind of to tell you that these are all linked concepts, and there's a very broad history to the things that we work on within the lab that are still highly relevant today to you as young researchers. So to give you an idea of where kind of these changes of phase between, you know, solid and liquid and vapor, vapor to solid are very important. These are kind of examples to give you a vignette of the different things that we work on within the lab. So the top left here, this is a image of frost formation and icing on a surface. And what you're looking at is a top-down view. And you know, you first have condensation, which are these spherical liquid droplets, and then you have supercooling, and frost will actually propagate across the surface and inundate your surface. And that's actually not very good for heat transfer at all. So what we work on within the lab is actually to make these non-wetting surfaces, like I mentioned, that could actually delay frost formation. And we get inspiration from nature via kind of those cicada nanopillar features that we structure onto the surface. In addition to that, you know, in the middle here, you're seeing an actual heat exchanger, which we've made completely super hydrophobic in a really scalable manner. And, you know, whenever we're working within the I-MRSEC on 2D materials and fundamental science, it's also very important to know how to translate that to large scale applications. And in this case, you know, we spent a lot of effort looking at how can we scale this up to actual installations that could help save us a few joules here, a few joules there, and make things more efficient. In addition to that, you know, electronics cooling. This is a wide band gap semiconductor material, a gallium nitride device. Think of this as something which is used to convert power in an electrified vehicle. You know, when you're charging it, you plug it into your outlet. It's 120 volts AC. You need to convert that to DC power. Your power converter does that, and it uses this material to do that. And the material heats up, and you have to actually remove the heat. And in this case, we're using these kind of interesting materials to cause droplet ejection, and then those droplets can actually deposit onto the hot surface and cool the surface, and therefore make it more efficient and operate for longer periods of time before failure. And then, you know, I mentioned condensers for power generation, and James Watt, and you know, his fundamental contribution to society was, you know, developing the Watt steam engine, but he did that by actually mainly working on the condenser. And in this case, you know, we're working on making surfaces where we can condense things other than steam, other, you know, petrochemical fluids which are relevant, things like ethanol, hexane, feedstock materials that are very relevant to society, not just in terms of, you know, fuels, but also materials for like t-shirts or polymers or plastics. And then on the bottom left here, I have an example of, where we don't just stick to low temperatures, we also do high temperature processes, where this is actually brazing of 2 copper plates. And by surface structuring the plates, you could actually enhance braze flow and make it go where you want it to go. So within our lab, we tend to span many different fundamental phase change processes, and over a wide range of length scales, a wide range of time scales, and a wide range of temperatures. So it's a very broad area of research that we conduct as a lab. But for today's particular talk, I'd like to mainly focus on kind of this icing behavior to give you guys a flavor of some of the icing work that we've been doing. And I won't belabor this slide. You guys will have access to these. Pam, I could actually make these available to the students, but this is just more kind of work on thermal management of electronics. The top left here, you're seeing an actual power conversion board dipped in water, and it's converting 2 kilowatts of power. So in this case, by using very thin coatings, insulating coatings, you could actually now enable cooling with fluids, which can be electrically conductive, but not worry about shorting or failure. And so think about this as, people tell you never use your electronics components or your hair dryer in your bathtub. That's obvious because you could have current leakage and you could shock yourself. In this case, we're actually doing it directly in a bathtub by actually dipping it into this fish tank of water. So let me move on. So why is all of this important, and why are surfaces in particular important to all of these processes? I've mentioned that we tend to get inspired from nature, and we tend to work with surfaces to structure them or change their chemistry. Well, it turns out that actually the way you treat the interface is very important to really fundamentally controlling the transport mechanisms which dictate whatever phase change process you're interested in. So to give you an example here, right, you can make a surface what we typically term hydrophilic or super hydrophilic. That means water loving. So if you deposit water on it, water will just spread uniformly and wet the surface, and you'll have a nice thin film. You won't even see a droplet on the surface. And you could change this and range all the way to what we call super hydrophobic. And in this case, if you put the droplet on there, this is like that cicada wing example. The droplet will just roll off and it doesn't want to stay on the surface at all. And it turns out that, depending on what you want to tackle, if you want to tackle biofouling or corrosion or icing or heat transfer, you really have to control this parameter of wetting a surface structure exquisitely to really get you optimum results. And so in addition to knowing the kind of fundamental science which dictates these transport mechanisms and then how to alter it, we also have to understand how we could make these surfaces and make them in a scalable manner such that we could actually make societal impact. So to give you a particular example, this is actually a nice motivating example to show you the power of the interface. So, I mentioned the super hydrophilic surface, highly wetting, thin liquid films. This is actually a copper tube where we're condensing steam or water vapor on the outside. So think of this as just like a cold tube, and then out here you have steam, and you're allowing that steam to condense into water. And you can see that when it condenses, it forms this very thin film, and you can barely see any droplets forming on here. You actually see a droplet going, I'm just trying to play it here. You see a droplet rolling down the middle towards the left. That's just because this tube is slightly tilted. So the film actually accumulates and moves to the left. Now, if I told you you could add a one molecule thick layer, so you're adding 1 nanometer of thickness layer on top of this tube on the outside, this is actually what will happen. So you'll actually start undergoing dropwise condensation. And so in terms of bang for your buck, right, the amount of material that you're actually adding, you're only tailoring the interface. You could actually transition from these 2 drastically different modes of condensation, where this middle mode here actually gives you a 10 times improvement in heat transfer. So you're getting 1,000% improvement in performance for adding 1 molecule layer onto your surface. And that's essentially the power of the interface, and hence why we really focus on it. Whenever dealing with these transport mechanisms of phase change, the interface is very, very important. And I think this is a common theme that you guys have heard as REU students in the I-MRSEC, hence why the MRSEC is so important and 2D materials are very important, mainly because of this, right? They just apply such a big impact on many fundamental processes. And then in addition to that, if you add structure, you could undergo what's called droplet jumping condensation. And my PhD was this is actually videos from my PhD work, where, the condensate doesn't want to stay on there at all. This surface is kind of like that interesting bug surface that I showed you, the cicada wing surface, where, you'll condense and droplets will just eject spontaneously from the surface. And so there's been a lot of work on tailoring this interface and kind of really showing how it could be used to enhance particular applications. So, but before I go too far in depth in terms of the scientific details, I thought I'd step back and talk a little bit more about fundamentals of wetting and what it actually means when a liquid comes in contact with a surface, and why some of these properties, why some of these surfaces have these particular properties. So I think many of you as students have heard of the term surface tension, and you think, water has a certain surface tension, and that's actually different from different working fluids like ethanol or alcohols or wine that maybe you're not consuming quite yet, but maybe you see your parents consume it. And the fundamental thermophysical property of surface tension arises simply because if you think about the molecular interactions of water in a droplet, and here on the top here, I'm showing a droplet with, you can think of these circles as water molecules. The molecules in the bulk have a very different interaction potential that's the same, essentially, any direction they look at. They have the same kind of pull or polar interaction with their neighbors. That's not actually true for the molecules which are at the interface. So these molecules on the outside will have an interaction with the bulk molecules that are on the inside of the liquid, but on the outside of it, they're actually interacting with air molecules or water vapor molecules. So you could think of them as being unhappy. You could think of them as being, they're not in equilibrium. And hence why this property of surface tension arises, because of this non-uniform force balance on these molecules. And it seems like this liquid now has this, mechanical property of almost requiring a force to break through the fluid, which is very unusual. It's almost like a solid at some length scale. And so what you could do with this is, you could actually tailor surfaces to utilize this property, especially for higher surface tension fluids, to have non-wetting, in this case, a droplet hitting a superhydrophobic surface, and have these highly spherical non-wetting states. So this is actually a needle which injects liquid water, and this down here is a superhydrophobic silicon wafer with a surface structure called black silicon that's been functionalized. So how do we actually achieve this, right? How does hydrophobicity work? Well, I think if you go to the kitchen, you'll notice that if you take, something like a waxy material, or for those of you who may own a vehicle and may, clean your car sometimes and give it a nice waxy, shiny finish, you'll know that, water tends to beat up on these materials. And it turns out that the reason this happens is because you're actually adding a thin molecular layer of a fatty acid in terms of your wax or in terms of things that you work with in the kitchen. But in this case, we call them self-assembled monolayers. And essentially all these are long chains of carbon-hydrogen bonds. So these are carbon-carbon bonds with hydrogen sticking out, or carbon-carbon bonds with fluorine. And all of what these molecules do is they're actually highly nonpolar. They're inert. Think of them as they don't want to interact really with anything. They're just kind of neutral. They just sit there. And what ends up happening is water, when you deposit it on top of this surface, it's not that the surface repels the water. It's actually that the water likes itself more than the surface. And this is actually a common misnomer with functional surfaces or non-wetting surfaces. Many people think that somehow you're adding a surface layer which is repelling water. That's not true. The water just wants to interact with itself more. And that's mainly because water molecules are polar in nature. If you look at the structure of water, you have two hydrogens and you have an oxygen, and the electrons want to spend time close to the oxygen more with the hydrogen. So you have dipoles form, and then you have many molecules and they reorient, and this is called a polar interaction. So hence, the misnomer here is the hydrophobicity. It's like, it's not necessarily that water doesn't like the surface. It's just water likes itself more. So, now what happens when we add structure to the surface? So in this case, if you look at water wetting a surface, the contact angle you make with the surface, this theta 1 here, is really dictated by the force balance at the contact line. So you have your liquid vapor surface tension, which is the thermophysical property I mentioned before of the liquid. But then you also have surface tensions or surface energies between the water and the solid and the vapor. And that really dictates this force balance, the three-phase contact line. And that's hence why, there's a famous equation called the Young's equation by a European scientist named Thomas Young, who in 1804 wrote this down for a smooth surface. But it turns out when you add roughness, you could actually have, extremes in wetting states. So if you have roughness of a certain length scale and a certain contact angle on the intrinsic surface, you could undergo formation of these Wenzel droplets dictated by the Wenzel equation, or what we typically see and what I've been showing you so far in the past videos, what we call Cassie-Baxter droplets. And these are actually two independent scientists, one named Cassie, one named Baxter. And they actually developed this in 1944, where they showed that if you have a highly non-wetting surface and then you structure it, you're actually forming more and more air pockets beneath the droplet. And because of that, this droplet is becoming more of like a suspended spherical droplet in free space. And hence, it'll take very, very high contact angles. These contact angles here can actually approach 180 degrees. So, if you want to think about this more from a fundamental level, right, you could think about the apparent contact angle or the intrinsic contact angle. So if you were to look at this is an environmental scanning electron microscopy image. So really zoom into that contact line region here at the three-phase contact line. You could actually see that intrinsically the wetting contact angle here is nothing but the contact angle with the smooth surface. But it's only the addition of these air pockets, these are actually pillars, that cause this kind of highly spherical non-wetting state. There's been a lot of work in this area in the past few years, mainly because of interest on how we could use these to dictate some of those transport mechanisms. So to give you an interesting example, this is actually an insect sitting on water. And I think many of you have seen this, when you go camping or when you go outside, if you look at a pond, you'll see many insects will be able to glide on water and stand on water. And actually the way to do this is if you zoom into their leg, you'll see their legs actually have these tiny small hairs. And it's actually those hairs that are actually functional. The chemistry of the hair is such that it's non-wetting. And the hair itself the surface tension of water is high enough such that the force of the hair can't actually penetrate the interface and go into the liquid. So the bug itself can actually be suspended on water and it could glide on water. And this is an interesting effect that nature utilizes all the time to really help insects breathe underwater or help insects, float on water, or plants such as lotus leaves float on water and not get wet. So you may ask, okay, well, why do we care? And that's actually a very good question. And like I mentioned, the surface is actually highly important to predicting the efficiency of the particular process. And so for after giving you all this motivation and background, I think I'd like to actually delve a little bit more into some of the icing-based applications that we've been working on to show you how these surfaces and interfaces can actually dictate the performance of the cycle. So I talked a little bit about droplet jumping, and I thought before I use this in the presentation, I should explain a little bit about how this process works. So on the video on the right here, what you're seeing is two droplets sitting on a superhydrophobic surface, and if they coalesce, you'll notice the droplets actually lift off the surface and jump. And you might say this is magic. It's actually not magic. Gravity's pointing downwards into the surface. And this is a high-speed video, so it's actually not this slow. This is 20,000 frames per second. So you're looking at 20,000 images per second played at you. Typically, what you're watching is about 30 frames per second. So this is highly slowed down, and so you can see the physics of what's happening. But and these droplets here are actually on the order of a couple of hundred micrometers, so they're much smaller than even a millimeter. So these are quite small. And so the way this process works, and the reason it could actually happen, is if you think about just an energy balance, the surface energy of two separated droplets is larger than the surface energy of one combined droplet. And it's this difference in surface energy that actually manifests itself into kinetic energy. And that kinetic energy is actually the energy of jumping, or the velocity that this droplet takes on once it actually departs from the surface. Now, to have this process happen, you actually have to have surfaces which are super hydrophobic or highly non-wetting. So the actual state of the droplet that it's residing on the surface has to have a very high contact angle and very low adhesion. And that's very important because if it has a high adhesion, the droplets will not depart. They'll actually stick to the surface. And so why is this process very useful? Well, it turns out in many applications, it's actually very useful to remove your liquid from the surface before it could freeze or before it could solidify or before it can accrete onto the surface and hinder performance. So this is where icing physics comes in. So if you were to look at icing, there's lots of beautiful things going on. This is a top view image. You've got nucleation, droplet dynamics. You've got freezing and vapor, freezing of liquid droplets. You've got condensation in areas, evaporation due to vapor pressure gradients. Lots of very interesting mechanisms, frost aggregation, that, I think at this point, given your background as REU students, we kind of skip over and look at how we could use this droplet jumping mechanism to really prevent ice accumulation and frost growth. So this kind of gives you a few of the different approaches of anti-icing work that we do within lab. And on the top left here, what you're seeing is a physical process we call deblooming. So in the regions where frost is actually coming off, those are super hydrophobic, and these kind of basal regions here are actually super hydrophilic. And so what's happening is as the frost melts, it'll actually want to melt into the regions of high wetting. So like you're seeing here, the black regions are non-wetting, and these gray regions are wetting, and you can actually see the frost will debloom or come into these wetting regions and really enhance the efficiency of your de-icing process. We also look at frost formation dynamics between surfaces, because in many thin surfaces, you have tiny gaps, and how the natural convection behavior occurs and how frost occurs is very important, and how these surfaces can affect that process. And then in addition to that, interesting projects like pulse defrosting, where you're really hitting the base of the interface, and this is an ice chunk. You could actually de-ice your surface with a very, very high efficiency. But pertaining to my talk today, I think, I kind of want to focus on this droplet jumping mechanism. And, the reason I pick frosting is because it's a very easy process to motivate in terms of the energy savings that it could offer to society. So, frost is actually a very big challenge to something called an air source heat pump. For those of you who aren't familiar with what air source heat pumps do, they're very common or very efficient ways to heat and cool your home in moderate or higher temperature climates. So all a heat pump does is basically you put energy into the heat pump, you put electrons in, and you do some work to move heat around. So think of it as like an air conditioning cycle, right, in the summertime. But in the wintertime, it'll also work by actually extracting heat from the cold air on the outside and putting it into your home. So you're doing work to move heat in and out of your home. And it's actually during this wintertime process that frosting occurs on the outside surfaces, because you are cooling already cold air, and frost can actually form and accumulate. And so, for example, for moderate climate zones like Memphis, where you would use something like a heat pump, you're talking about energy usage of 20 terabytes, or I apologize, 20 tera BTU British thermal units per year for residential, and 18 tera BTU per year in commercial usage, right? And so heat pumps are actually a big energy utilizer within the US. For refrigeration costs, you're talking about another 20 tera BTU per year. And in addition to that, current heat exchanger designs are done to actually accommodate this frosting process. So you're actually penalizing yourself in order to deal with this frosting. So if you actually add up all the potential energy savings, if you can make enhanced defrosting surfaces or delay frosting and icing, you could be saving yourself an extra 25 tera BTU per year in terms of primary US energy savings. And that's a big chunk, right? That's not trivial. So hence why our motivation to actually work on this frosting problem. So to give you an idea of what we actually do, we do this kind of very scalable surface structure fabrication. This is a process that we developed in lab. This actually works with aluminum, and you guys can try this at home actually, just be careful, don't burn yourself. If you take aluminum, you can do this with aluminum foil, for example, and you put it in warm water. And what I mean by warm water is like 89 degrees Celsius. You'll actually form an aluminum hydroxide. It's this AlOOH, which has this surface structure on it. Now, when you do it, you're not going to see it. But if you were to take this and put this in an SEM, you would have these kind of flower-like structures on the outside. And that's the beauty of this process, is that it's very simple, it's very cheap, it's very scalable, right? Dipping a large, very complex piece into water heated water is quite easy in terms of an industrial process. And then afterwards, we do atmospheric chemical vapor deposition to make this surface super hydrophobic, because after you form the aluminum, it's not super hydrophobic. You have to add that chemical layer on the outside to make the water like itself more than it wants to wet the surface. And you end up having this kind of highly spherical droplet morphology, which is actually great for droplet jumping. Now, the main reason why we choose aluminum is because aluminum is a very common heat exchange material. So many heat exchangers that you would see in industry are actually aluminum based. Copper is a better material, as many of you know, has a higher thermal conductivity, but it's more expensive. And so aluminum is the material of choice these days. And in terms of the experiments that we do, this is an experiment we run in lab where, we have an actual heat exchanger from a company. We make this heat exchanger super hydrophobic, and then we basically cool the heat exchanger by flowing a coolant through here, through these tubes, and we allow air on the outside to pass through, and that air is cooled, and hence why the air gives heat to the heat exchanger, and we're exchanging heat by the heat exchanger. But the air has moisture, so that air can actually now condense and frost on the heat exchanger, and hence why we could use this experimental setup to actually see what the effects of this frost formation are on both heat exchanger wettability, but also on heat transfer. And so to give you an idea of what this experiment looks like, this is an uncoated heat exchanger. Your airflow is moving from right to left in this case. This rod here is actually a thermocouple. It's a way to measure the temperature at this particular point. But right now, this is running an experiment. So the heat exchanger is being cooled, and you could see that you get a lot of moisture buildup on the outside. It's like, taking out your cold drink, your aluminum soda can on a hot summer day. If you leave it outside in your living room or even outside in your house, you'll see that water will build up on the outside. And that's simply because of moisture within the air. And so, on an unaltered heat exchanger, you'll have kind of liquid form, and the liquid will just drain off slowly from the heat exchanger. But on a super hydrophobic heat exchanger, you could actually see here that in some instances, you could actually see droplet jumping out of plane into the wind. And so here, droplets are much smaller, and they actually depart from the surface through this droplet jumping mechanism. And this is more clearly seen here on this infrared image, where you could see that, even though your flow of air in this infrared image is in right to left, you're actually seeing droplets eject the heat exchanger and leave into the airstream. And the main reason this helps frosting is because it's these droplets which accumulate on the heat exchanger that's super cool, that eventually ice up and block all the air passages and really make this process very inefficient, forcing you to run a defrost cycle. So to give you an idea of what this looks like in real time, these two videos on the bottom here are showing you two real-time comparisons of this frosting process. The video on the left is actually just the as-is heat exchanger, and the video on the right is a super hydrophobic one. And you can see that there's a significant delay in the frosting behavior on the super hydrophobic one, mainly because you're shedding the liquid very efficiently into the airstream. And so what this relates to, or what this equates to, is if you plot the heat transfer rate as a function of time, you maintain a very high heat transfer rate for the heat exchanger on the right here, which is super hydrophobic, but your heat transfer rate on a wetting heat exchanger, or as is, just decays because the frost grows on the surface, and you have very inefficient thermal pathways from your coolant to your air. And so this is actually, the bread and butter of what we do in the lab is actually prove these in a scalable manner to then use to have energy savings in real industrial systems, such as heat pumps, for example. So to give you an idea of where we are currently, this is actually a third-party validation that we've done with a local company called Creative Thermal Solutions here in Urbana, actually, and using a whole host of different collaborators, whether they be heat exchanger manufacturers or actually utilizers or developers of heat pumps. We've been able to show very efficient performance where you can imagine these curves, the higher they are, the better it is for your overall efficiency. So you could think of this as a temperature difference from indoor to outdoor when you're using that heating mode. And you want that temperature difference to be high because you want to maintain your home to be warm in the wintertime. But you could see that because of frosting, these uncoated heat exchangers will actually accumulate frost and they'll decay in performance over time. So we're very happy with these results. And this is kind of a very good proof of concept of the fact that tailoring these interfaces in a very scalable way can really affect your energy savings on your real life systems. So where are we now? Because of the spread of COVID and because this has been affecting so many of us, we've really been taking our expertise of interfaces and kind of fluid mechanics of droplets in wetting and really applying them to study how surfaces can affect the spread of COVID or the transmission of COVID. And, because we have so much effort on energy and heat transfer, buildings are, a prime example of places where COVID can spread mainly through the ventilation systems within buildings. So many of you may know, or you may not, that not all of the air coming into your office or coming into your building is fresh air. Much of it is actually recirculated or put back into the building after it's been reconditioned because of energy savings. You don't want to just dump out all that warm air or cold air to the outside. It's very inefficient. And because of that, actually knowing how particulates or droplets interact with heat exchangers or surfaces is very important, because you could have one occupant in one room, sneeze like it's shown here, and then these droplets can actually be entrained, go into your filtration system, and then come out and infect somebody else somewhere else. And so we've really been looking at how, particles and droplets interact given a certain velocity with surfaces, and how changing the wettability of these surfaces ends up changing these kind of interaction pathways, and how these, bacterial species or pathogens can spread via the HVAC system within buildings. And I apologize, by HVAC, I mean heating, ventilation, and air conditioning. So those are kind of two examples. I've kept them a little bit brief, but that's mainly because I wanted to move on to my second topic, which is, I think, more useful to many of you REU students, to give you an idea of, my background, what it is that I went through, and to give you a bit of advice, whether you're looking for it or not, on, some challenges that I encountered as a faculty member, as a student, as a young man, and things that, I could tell you to watch out for that may or may not help you. So in everything I say here, it's completely up to you to take it away, and anything I say that you don't want to follow, you don't have to follow by any means. Just these are things that work for me. So, I thought I'd start out by telling you all where I'm from. I actually grew up in a country called Serbia. It used to be called Yugoslavia. And, one common misnomer I always get is people always tell me that's cold, right? And so I tell people all the time, Serbia is not Siberia. They're actually very different countries. Serbia is this little green country in Eastern Europe. It's close to Italy, which is the boot here. Siberia is this giant landmass north of Russia, or part of Russia. But yeah, Siberia is very cold, I agree, but that's not Serbia. And so I actually grew up in Serbia. At the age of 10, I moved away. And to give you an idea of the history, this region has always been, a contentious region, many wars. Many of you probably know your World War I and World War II history. But at the time which I moved away from Serbia, it was actually a very difficult time for my parents and myself as a child. There was a war undergoing, and the country was essentially fractioning into pieces. And so from this large country called Yugoslavia, this formed 7 smaller countries, which are now kind of outlined here. And I'll kind of let you look it up if you're interested. But this is kind of the map of the country. And the main reason why it fractured was before, it actually used to be a communist nation. So, in terms of my background, I've had a little bit of experience with communism as a political system, and then moving on to Canada as a young man and the United States. So I've seen the political spectrum, and this is not a political talk, so I'm not going to comment on it. But this kind of gives you an idea of background of where I'm from, and the fact that I have seen more things than most people just growing up in the West. So in terms of science, many of you know this vehicle down here. This is a Tesla vehicle. The company has been doing pretty well. Probably many of you don't know that Tesla is actually a Serbian or Serbo-Croatian inventor. He actually grew up in Serbia and moved from Serbia to the United States to work for Thomas Edison. And then he actually did most of his inventions and most of his contributions of electrification of society with George Westinghouse in Pennsylvania, Westinghouse Electric. And so he's probably the most famous Serbian inventor, most famous Serbian scientist. He's so famous that we have him on money, right? And I think if you think about the US, we don't, or even Canada, we don't tend to put people of scientific background on money, which I think sometimes we should. His claim to fame is, for those of you who don't know him, is mainly electrification, electric motors, alternating current power transfer, AC power transfer. So, all of the electrons you're getting out to your devices, to your iPhones, iPads, your electric vehicles, the way those are transferred and the way we use them, a lot of the initial work was actually done by Nikola Tesla. So, in terms of the culture, where, kind of in terms of food, it's just like a very bland culture. I kind of grew up in this middle region of Serbia, and this is actually a picture of me when I was a kid. My camera's not on now, so you can't see how I've grown and how I've aged. But yeah, I've got one brother, and we were kind of a very middle-class household that, just the family was always tight-knit, and we always kind of enjoyed being with each other. And, in the 1990s, we actually moved to Canada. So here I have 1990, but it's actually 1995. We moved to Toronto, and, from the age of 10, I lived in Toronto and grew up there. I went to elementary school there and high school there. And, some good things about Canada, which I think many of you know, it's free healthcare, education is free. It's a very liberal country, very progressive in nature. Some bad things are it's cold. You're going to pay high taxes. So if you're okay with that, it's a good place to live. And pretty much the only sport that we follow in Canada is hockey. I know the Raptors are pretty famous after last year. I was very happy for them. But, this was a big move for myself as a child, moving continents. And so it was a big experience, but a very, very positive one. And so, growing up in Canada, it's a great place for any of you REU students who have the chance to travel. I know with COVID, it's a little tough. I highly encourage you to try to visit. Lots of great things to see. One common thing people don't realize is Canada has the longest freshwater beach in the world. If you go to Wasaga Beach, it's north of Toronto, it's just a beautiful place to go swim. Very shallow waters. It's almost like a piece of the Caribbean in Canada. So in the summertime, it's a great place to be. So for my undergraduate, I actually went to the University of Waterloo. It's a small school in Canada. Well, not small school, but it's a smaller school than the majority of the schools that you guys attend. It's a great program in terms of famous alumni. Chris Hadfield, he's kind of a famous NASA astronaut. But the great things I really got from the Waterloo program was its co-op structure. And by co-op, that's essentially a structure where you go to school for 1 semester and then you do an internship for 1 semester and you alternate that way for 5 years. So by the end of it, you end up having 2 years of work experience in a variety of different places, coupled with a 4-year degree. And there's no summers, there's no time off. You basically just keep cycling through until you're finished with your degree. And so, again, great things, co-op program, essentially free education. And it's a great education. We call it the MIT of the North, but it's essentially a competitor to MIT if you think of the schools in Canada and the schools in the US. And so it's a highly technical school, lots of engineering programs, accounting, computer science, mathematics. The bad things were it's the middle of nowhere. It was developed in 1957, which was during the middle of the Cold War. So many buildings were very ugly. They were functionally designed. They weren't designed to be pretty. And it's very cold. So I warn you, don't go there if you don't like the cold. So the co-ops for me were actually super awesome. I really enjoyed them because they really exposed me to different sectors of industry. And that's really what helped me decide whether I want to do, a graduate degree or whether I want to go into industry after I finish my bachelor's degree. And so the first co-op I did actually relates to a lot of the work that I do now. It was HVAC in our company, heating, ventilation, and air conditioning. And I was doing a lot of kind of design of these HVAC systems and sales and going out and startup and maintenance with technicians. And this really opened up my knowledge field or view of heat exchangers and heat exchange and how important energy is to buildings. And so, after doing 2 semesters at this company called NMAR in Toronto, I ended up deciding that I needed a change and I wanted to experience something else. And that essentially led me to my second co-op experience, which was with a company called Husky Injection Molding Systems. And many of you don't know this company, but this is the #1 manufacturer of injection molding machines across the globe. They're based in the Toronto region. But essentially every, Pepsi or Coke bottle that you buy, or any drink bottle that you buy that's PET, recyclable, it's actually made by a Husky machine. So basically Husky was a great experience for me. It really opened my eyes. My first semester there was in the patent division. So I got to see how patents are formed and made and how inventions are disclosed. And then my second experience with Husky was actually in their R&D division. I actually switched teams and I really got exposed to research and development and how the scientific method is conducted within an industrial setting. And what is it that we're really trying to get out of R&D and how we're trying to grow companies using an R&D infrastructure. And so, the things that I noticed that were very important for me during these co-ops, when you're working with R&D, the work was very stimulating. So you're always thinking, you're always, on your feet. But also you have more freedom to choose kind of what next steps. It's less structured. It's less of a monotonous environment. And I also noticed that many people within the R&D framework have graduate degrees. So they have master's or PhD. And so that's really what made me think after this experience, maybe I should go into grad school. Maybe that's something that I should be interested in, given that I'm enjoying this experience. And then my last two co-op experiences, there was a total of 6. The last 2, I did it with a consulting company. It was technical consulting. It's called Hatch. And they're another big company in the Toronto area that does mining, minerals, and energy consulting. And here I got exposed to simulations, as well as kind of energy knowledge of how energy intensive the mining industry is. And so, I had a lot of interest in kind of these simulations. When I was an undergrad, I would see a lot of them and I would say, oh, awesome, fluid flow, pretty pictures. This is great. You could like simulate real life in your computer. And, working at Husky, I realized more about the limitations of simulations, and it also exposed me to this method and how you could use it to kind of supplement your knowledge and help you with research. And again, the work was very stimulating. And I noticed the same thing as it did in Husky, is that most employees and most of their bosses actually had PhDs or doctorate degrees. And it was actually after this experience that I realized maybe I should go ahead and get a doctorate degree or a master's degree to start, because that's going to help me get a position in some of these companies that's a little bit higher up, that'll give me some freedom to really do what it is that I want to do and enjoy it. So the big takeaway here after all these co-ops was industry jobs are fun. But rarely are they as fun as the ones where you have a graduate degree. And so that actually led me to graduate school, and grad school was great. I went to grad school in Boston at MIT. It was great people, essentially free education, great education. I met my wife there. So I met my life partner. We're still married. We have 2 kids, and great travel opportunities. So if you're interested in really having, a time in your life where you're going to have intellectual freedom to learn as much as you can, and if you enjoy learning, I highly encourage you to think about getting a graduate degree. In terms of the bad things, Boston's cold. It's too intense at times. There's a lot of competition between students. So think about where you want to go for a graduate degree. And this is actually where I encountered my first challenge that many of you may encounter if you do want to go to grad school, is how do you choose an advisor? And my advice to any student that I meet with today is choose the advisor, don't choose the project. You may have a passion in energy, you may have a passion in mechanics and fluid mechanics and nanotechnology, but if you don't have the right fit with the person who's going to be guiding you for the next 5-6 years, it's not going to work out very well. And so, when I went to interview with advisors at MIT, I actually had this challenge directly, meaning that one person who gave me a full-time offer was known to be quite a difficult advisor. I'll say it lightly, difficult. And one advisor who didn't quite have the funding for me, but only had kind of partial funding to start, was known to be very nice, and we hit it off very well. And, I remember having a conversation with my parents coming from Canada. my parents were very middle class, and paying for an education within the US was very expensive. And it was a very contentious issue in terms of like, who do I work with when I go to MIT? And my parents were very worried in terms of the costs associated with not having funding. And, luckily I made the gut decision to go with my advisor that I chose, which was the nice person. And luckily she found funding and everything worked out and everything was great. But, I tell everybody today that I know way more stories of people choosing advisor or not choosing advisor and choosing project that they end up getting burnt out, or, they should have listened to their gut feeling in the long run. So that's kind of my broad advice to you as students, as REU students is, and, whether you go to academia or work, it's the same message. It's much better to find a good team that fits well rather than to go work for a company which, the team may not be a good fit, but it's a brand name, for example. And so I give the same advice to all of my students, whether they're graduate or undergraduate. By the way, these are actually images of parties that we used to have in graduate school. And a lot of these people are faculty now. This guy is at UNLV. This guy's at Santa Barbara. Amy Marconet is at Purdue. George is still doing his PhD, and Lee is still doing his PhD as well. So again, the good things, just to reiterate, lots of freedom to pursue solutions of relevant problems in your own way. Essentially, it's a free education, so take advantage of it. And vacation time is a lot more flexible. In terms of the bad things, the freedom can sometimes be a little bit too much, so that's a challenge. And so you're gonna feel like you're lost in the woods, and many people won't be able to help you. So you're gonna have to kind of do your own reading and do your own discovery. It can be demanding and intense at times in terms of deadlines, and this really depends on your advisor, and hence why it's important to choose the correct advisor. And it's actually difficult to leave your work, meaning that, in a company job, you could leave at 5 and go home and enjoy your time and spend time with family and do whatever it is that you want to do. Whereas in academia, you're working on problems that are constantly on your mind and you're constantly trying to solve them. So if you're really passionate about them, that's actually fantastic. You're always enjoying yourself. But you could actually find it sometimes that it's a little bit too much and it's hard to actually disconnect. So, I put together these next few slides. I'm going to go through them quickly, but I wanted to give you guys an idea of academia versus industry, if this is something that you guys are considering. And, I say here after PhD, but you could actually apply this even before PhD. So you can think of this as going into an academic route versus going into an industry route. And there's kind of 9 or 10 different bullet points here. I'm not going to go through all of them just for the sake of time. I want to leave some time for questions. But, I've broken it down in terms of location flexibility, time flexibility, in terms of your office space, the privacy, in terms of the money you can earn, coworker camaraderie, credit, meaning, I don't mean like credit card, but I mean like the work that you do in an academic setting belongs to you and you will be recognized for it. Whereas work that you do in industry, you may not get the exact recognition that you are expecting. And that's a common theme that I hear from students that end up leaving and going into industry. Directness of effort, directness of impact, and sense of control. And I'm going to make these slides available to you, so don't feel like you have to read them now. You could actually see all the videos and all the images afterwards. And you could always follow up with me with email. Pam has my email contact, and you could ask me any questions you have. So I guess the last thing that I wanted to talk about was these kind of 10 commandments or pieces of advice for you. No person is an island. They used to say no man is an island, but I understand today, we should say no person is an island. Use those around you for help. You're not alone. Sometimes luck is involved in life, and not everything is done just based on your hard work. And sometimes it's with you, sometimes it's not. It's important to stay positive, and you can't always control everything within your destiny. Or experiments for that matter. So in this case, I mean this in terms of experiments in the lab. If you do end up going into grad school, you're going to have days where you're not lucky, but you're going to have days where you're lucky. And so in the long run, it equals out. Don't get discouraged. It's nice to be important, but it's more important to be nice. This is just general advice I give to everybody, including my kids, like all the time. Be appreciative of those around you. Everybody around you is working to help you, and you're no more important than they are. Collaboration and openness is always more beneficial than being secretive. Don't be afraid to share. Don't be afraid to share your work and tell people feedback and tell them what you're working on. While at school, make as many connections as you can. I think I mentioned that many of the colleagues that used to come to parties and were my friends are now very important colleagues in companies in academia. And I could always lean on them for advice or for help. And so it's very important to make those connections. And all of you as REU students right now should stay in contact and keep those connections over the long run, because you'll see it'll be very beneficial, 10, 20 years down the road. There is no such thing as a stupid question. This is just the most common thing I tell my class patrons. Just ask. Trust me, many other people are thinking the same thing. When experiments are working, don't stop them. Stay up all night. You'll see many advisors will tell you this. This is mainly because experiments don't always work out. My advice is take 4 weeks at least vacation per year. You need your time to rest. Don't tell any other advisor that I told you this because I may get in trouble, but with my students, I tend to give them time off because I was given time off as a grad student, and it was really beneficial for me and my development. And then get your sleep. Sleep is very important. I'm sure your parents tell you this all the time. I'm kind of going to be a parent here and tell you the same thing. Trust me, in the long run, it's very, very important. And then, yeah, this kind of just shows you the people that I met. This is actually my PhD group, and this is my postdoctoral group at MIT. And you can see I've made fostered connections with all these people that I could always lean on at any point. And so they were really instrumental in my development as a faculty member. In this particular case, at least for the icing performance, you actually don't want water contact at all with your surface. So the increased surface area of water allows you to have more surface energy. And by having more surface energy, you could have more kinetic energy transfer and more jumping and less water on the surface. But you are right that in many processes in heat transfer, surface area to volume ratio is very important, and smaller droplets or more spherical droplets are a lot more beneficial than droplets which are highly wetting or films. And so that's a good comment. It's a good insight. Yeah, that's a good question. So I think the most important thing, not necessarily a skill, but the most important thing to develop through internships is to identify what is it that you have interest in. So what is your, I don't want to say passion because you could have multiple passions, but many times students come in and they finish and they're excellent students, but they have this thing called paradox of choice, meaning that they're good at everything, but they don't really know what they want to do. And so, for myself, I had a lot of experience with thermal systems, with heat transfer. I also found I was interested in it, but I also did well in it in classes. I did a lot better in terms of heat transfer than I did with control theory or microprocessing or computation or programming, for example. And so for me, it was like a natural transition, and I've always known I wanted to do that. And so the industry internships really helped that. In terms of skills, I would say, basic skills with, I wouldn't even say coding, for example, but if you have access to simple coding, C++, C, MATLAB, those become very useful as a graduate student, because many times when you are analyzing data, knowing how to process data is very important. Very simple kind of introductory statistical methods. So when you do have data, knowing what it means. And then, simple things like knowing how to use Excel, for example, or, Microsoft Word, putting together documents, knowing how to write a technical report. Those are all very important skills that'll help you as a student because the research is one side, but then when you have to write up your research, you have to have the ability to write a research paper. And that takes a lot of time to develop. And that's one big advantage over students that are from the West that they have over international students, which take a little bit longer to develop. So I would say, as you have these internships, learn as much as you can in terms of basic science and find your passions, but also learn some of these kind of very simple methods that we all use and simple software that we all use that will be very beneficial for you. There definitely is an impact. And I won't lie, I won't make it seem like, oh, there's no impact at all. Getting into a good program, especially if you want an academic job, which here you're saying an academic job, it is important to find, a top program which will foster you and allow you to publish that doesn't mean that, you know, the inverse is untrue. So it doesn't mean that if you, just because you don't go to a top school, you're not going to find an academic job. And there's plenty of instances where people that do go to top programs don't do as well as they could have done if they went to a lower ranked program. And so my advice is, if you have the chance to go to a higher ranked program, do it. Don't say no just because you may have some fear, or you may have some, you know, hesitation, or you may have some comfort towards going to a school which is, you know, like closer to home, for example. I would always encourage you as a young person, take the risk and you know, have confidence in yourself. But yeah, school ranking is relatively important, but it doesn't mean that you know, you're going to have no chance in getting an academic job afterwards. I think the main things that are going to differentiate you are hard work, the kind of advisor you have, and how well they foster you to grow as a person. You know, when I went to grad school, I didn't know that I wanted to do academia. And many people are surprised when they hear that. I didn't know until like my last year. And the only reason I knew is because I went to a conference, and a faculty member here at Illinois saw me give a talk and essentially asked me, "Are you looking for a job?" And it was kind of a coincidence. And, you know, I know it's rare, but the job kind of fell in my lap. And I was very lucky in that. And that's why I say sometimes you have luck, sometimes you don't. And they had asked me to apply, and you know, because of the process and the time of year that it was, everything went very quickly, and I had this job locked up within like a month. And so for me, it was never a fact of, you know, at some point I learned I wanted to do academia versus industry. I was very open to both. And it was just the fact that simply, you know, I had this offer, and Illinois is a fantastic school. I think many of you know that. And I just said, you know, it's too good of an offer to pass up. I'd like to try it out. And, you know, I've been here ever since, and I've been very happy. It doesn't necessarily mean that you're going to be unhappy in industry. There's many of my colleagues that went to industry and are very happy right now. So that was kind of my path, and it was kind of serendipitous. Personally, myself, no. I mean, if there's a certain area that you are passionate about, you should go to the school that has the top program in that area. Maybe the school is not as highly ranked. Let me give you an example, right? Illinois, we are not very well known for oceanographic research. We don't have an ocean next to us. So for example, if I had the chance to go to a school on the coast, maybe not MIT, maybe Northwestern, or sorry, Northeastern, as opposed to Illinois, because they may have a better subtopic that I'm passionate about, I would do that. That doesn't mean that everybody would do that, but that would be my advice to you is if you really have a passion in a certain topic or a certain area, and if you're sure that that's something you want to pursue, go to the school where you're going to get that. Don't just go to the name brand school just simply because it's a name brand. So that'd be my advice, Diana. Hopefully that helps. Okay, thank you, everybody. Hey, have a good rest of your day. Enjoy the weather.